Good evening, everyone. Thanks for being here this evening. My name is Sandy Barr. I'm the director for Sierra Club's Grand Canyon chapter. That's the Arizona chapter. I use she, her pronouns. And I am very pleased to be here this evening to talk about something with you all and listen, mostly. Something that I'm very passionate about and that the Sierra Club is very concerned about. Before I introduce our panelists, I wanted to introduce a couple of other folks that are here. Matea Getz, who is our Grand Canyon organizer, and if you're interested in getting involved locally and organizing events and activities, please connect with Matea. And Anna Gorla, who is our public lands and energy organizer. Anna is based in Phoenix with me, but we spend a fair amount of time organizing on issues up here as well. And then we have Taylor McKinnon with the Center for Biological Diversity. They are a co-sponsor of tonight's event. And then Kelly Burke, who is with Wild Arizona, also a co-sponsor of tonight's event. And there are some organizations that weren't able to make it here in person. National Parks Conservation Association is also a co-sponsor. And let's see, where is Sarah Key? Oh, right here. And then Arizona Faith Network is also a co-sponsor of tonight's event. And wanted to also introduce Stuart Chavez, who is a member of the Havasupai tribe and on their uranium committee, and just a fierce advocate for protecting the Red Butte area and the national monument out there. So anyway, I probably forgot someone, and I will apologize ahead of time, but I just wanted to thank you all for being here. And before I introduce the panelists, I just wanted to say that there are a few things going on with the Pinyon Plain Mine that maybe you haven't all heard about, so I just wanted to make sure you had the most recent information. One is both the Attorney General and the Governor have asked the Forest Service to do new National Environmental Policy Act review, so supplemental review. The review that was done, the environmental impact statement that was done, is from 1986. It was dated when we challenged it in 2007-ish, and it's even more dated now. So we're hoping that we'll get a response from the Forest Service on that soon. And then, as you probably have seen, there have been a number of protests, both near Red Butte, and there was a prayer walk last week to Red Butte, and then there have also been protests in Cameron. And the Navajo Nation has also expressed its opposition to hauling uranium ore across the nation, and of course is opposed to this mine as well. So I think those were the main updates. We're still collecting signatures on a petition to I'm always too polite. Demand that Governor Hobbs help us shut down the mine. We think she should use the authority that they have at the Department of Environmental Quality relative to the Aquifer Protection Permit. And then we're also sharing that with the Biden administration and asking them to use their powers. We are not okay with a pause. We are not okay with just a pause. We want to, unless you want to call it a permanent pause, then we're okay. So that's what we're looking for. So anyway, enough from me. You came tonight to hear from some great experts. We're so pleased to have with us Dr. David Kramer, Dr. Laura Crossey, and Dr. Karlstrom. And these folks have done so much work. They won't be able to talk about even this much of it tonight, but they know a lot about the geology and hydrogeology of the region. And so I am looking forward to hearing what they have to say, and I know that you will all learn a lot. So with that, Dave is going to kick things off.
Thank you very much, Sandy, and it's great to be here. What we'd like to do is have a really interactive group, and a lot of that will be at the end. So if you have questions and things like that, we want this to be interactive. A little bit about myself before I start. Dave Kramer, University of Nevada, Las Vegas. First time to the Grand Canyon, 1963, before a lot of you were born. My first hike down was 1971 down the Bass Trail, and since then I've been down just about every trail and bushwhacked to these god-awful places to sample springs at their source. In 1983 was my first river trip when it was flowing 52,000 CFS when we started, went up over 1,000. I was on a private trip in a kayak. I was the only kayaker I saw on the whole trip, and those of you who have read the Emerald Mile, they went past us down below lava. In the late 80s, I began researching the springs of the Grand Canyon, doing isotope work, doing all sorts of water quality analyses to see if there would be an impact from Tusayan and things like that. In 1992, I testified before ADEQ, the Arizona Department of Environmental Quality. I was worried that when the mines hit upper aquifer, that there'd be a lot of water there. We were assured by the mining hydrologists that this would not happen, but in 2016 they hit a gusher. In 1995, my research group, myself and Jim Fitzgerald, we found high uranium below an old uranium mine, lost orphan uranium mine up on the rim. It was the first group to really find high uranium above the standard. And then in 2012, I got the opportunity to testify before Congress. I testified before the Nuclear Regulatory Commission, and I've also gotten a chance to address the General Assembly of the United Nations on these sort of topics. So that's my background. We've been even up until last year, one of my students did some research and found that there was still high uranium in the springs in Horn Creek below Lost Orphan uranium mine, which closed in 1970. So without further ado, I'd like to go on, and as leadoff hitter here, I'm just going to do some general information and generally why scientists are concerned with uranium mining close to the Grand Canyon. So this is stuff you know. Why are we concerned about spring sustainability? And it's for recreational uses, of course, for long-term indicators of spring health, and there's all sorts of indicators there. Oh, boy. I'm really fast here.
Suddenly go fast and that goes backwards.
And it's not going back either. Oh wait, it's going forward.
We're still up there.
Point it this way. Okay, there we go. They just don't give out these PhDs. All right, so most people know the reasons why we want to protect the springs of the Grand Canyon. All 11 Native American nations and tribes are opposed to mining, the cultural heritage and other reasons. And that's a circle dance going on down in Havasu this last spring. Actually, this is up in Nebraska. They have uranium mining problems up there as well. So the type of mining that's going on is called breccia pipe mining. And so the first question is, what's a breccia pipe? Now, how many people know what a breccia pipe is? About 2/3. Okay, so the boatman on the river asked me, can you smoke it? And the answer to that is no, you can't smoke a breccia pipe. But how did uranium get in? We'll just quickly review how that happens. What happens is there's a lower aquifer, the lower Redwall Mauve, and an upper aquifer. The lower aquifer is where some of the main springs of the Grand Canyon come through, and the upper aquifer is in several different geologic layers. If you look at, if you hike down the Bright Angel Trail and you see this little icicle-looking thing, it's travertine. It indicates that water was at that contact between the Hermit and the Coconino in the past. And so there's a student sampling from dripping springs from that contact. So how do betropipes form? In geologic history, you have a collapse feature. You have a cave that is developed, and this is the red wall limestone down near the Bridge of Sighs, for those of you who are river runners. It collapses into a chimney of broken rock. That's what breccia means, it's broken rock. And so this collapses into a chimney, stopes upward to the surface, causes a surface depression, and sometimes surface water follows the depression, sort of connect the dots. Water in geologic history flows up and down these things. When water hits a low oxygen zone and it has dissolved uranium in it, it becomes ore. It chemically precipitates and becomes solid. The opposite is true. When there's a lot of oxygen, the solid material can actually dissolve into water. So the low oxygen zones are the Hermit Shale here, and the Supai Formation, and actually into the Red Wall as well. That's how the uranium gets there, and that's where the mines want to go. This shot is actually in the Red Wall limestone here. It's in Horseshoe Mesa. If you were to hike the Grandview Trail, there's a prospect right there. If you were to take a Geiger counter into the prospect, as I have, it kind of goes off the charts there. But you can see copper, it goes all the way down into the Red Wall limestone, and it follows fractures and faults. This is Pinyon Plain Mine, used to be called a canyon mine, and that's the one we're concerned about. And here they're misting water into the air because the evaporation pond can't hold it, and that was in 2016. I'm going to skip this one here. This just shows the different levels, and we'll leave this and talk about that later. So, what are our concerns? First, exploration holes have gone in the 1980s. And so I'm going to show you some of those, not all of those. But if you notice some of these exploration holes that are drawn in here, they go down to the Red Wall limestone. And then there's a supply well that goes down. Most hydrologists know that one well is a monitoring well is insufficient to sample. If it's up gradient of groundwater flow, pollution can actually flow down gradient. And if you pump it real heavily, it could pump from clean areas and dirty areas, and you'll get a false negative because it'll look cleaner than it really is. Then a major shaft goes down about maybe 12 to 1,400 feet, and there are side borings off of that to see where the high uranium is. I can't draw them all on here, but there is more than 17.5 miles of boreholes. These are open boreholes that allow water to move through as conduits, so they're added conduits through. Then the mining process puts in a spiral tunnel, so actually vehicles can get down there and they can extract ore. There are horizontal shafts that come off that. That's illustrated here. And then there's large cavities that are cut out. So that's what the mining process looks like. The one thing I want to mention at this point is that there are a lot of breccia pipes in the Grand Canyon area. The yellow ones are the ones we know about, but in 2015, the Arizona Geological Survey said, they asked the question, are there breccia pipes there that we don't know about? So they took two squares, and down in this lower square here is where Canyon Uranium / Pinyon Plains Mine is located. And one of my concerns is that if you have a breccia pipe right next to, oh, by the way, this is the new national monument around the Grand Canyon here in the red, so it's in the same area. In this, what I want to illustrate is if upon mining activities or closure, water in the upper aquifer can go over to one of the nearby breccia pipes, it can then move up and down that nearby breccia pipe. And none of the nearby breccia pipes have been explored by the mines as far as their potential for vertical movement. So here's Pinyon Plains, there's the Grand Canyon rim right there. And it was mentioned that the 1986 environmental impact statement is the one that people use to evaluate, the mines use to evaluate whether or not there's going to be a problem. Come on up, guys. And in that document, they use the term layer cake geology. So we decided to do sort of a fun little analogy called the Bright Angel Food Cake. And so this is our Bright Angel Food layer cake model. And the mines did complicate it a little bit, and I'll show you their complication. There's the breccia pipe there, and they tilted it. They took the cake and they tilted it, and that's the way the layers of the Grand Canyon go. They go south to southwest downhill or down dip toward the Havasu Canyon recharge area where water feeds the springs of Havasu Canyon. If you go north-northeast, you go to the Grand Canyon in the Grand Canyon sequence. That's the first complication they have. And the second one is that there's an aquitard layer at the bottom of the supai that's drawn in here that's low permeability, and water can't go between the aquifers. And there's abundance of evidence now that will be shown that this is not true. So this is the mine's simple layer cake model in the 1986 EIS, which is a lot of people have used. And if you're don't look into it in depth, it's simple and easy to swallow, this cake.
Just one.
All right. Now, let's do the real complications of this cake now. First, let's draw in the aquifers. There's the upper aquifer, which is the Kaibab, Toroweep, Coconino, and Supai formations, and the lower aquifer, which is the Red Wall, Mauve limestones. And then there are multiple lines of evidence that I think Laurie and Karl might talk about, that these upper aquifer and lower aquifers are connected. The USGS has done a lot of work on this recently with isotopes. There's been dye tracer tests that show that there's movement vertically between these, but the mines don't, they say that these are separate. Let's add some folds and faults. We'll take the layer cake and we'll start bending it. So here's the Ermita and Grandview monoclines, which is a bend downwards, and we'll do the cataract syncline where it actually collapses down. If I can forward here, it's a little slow. There we go. Okay, so we're making the cake a little bit more complicated. Now, if you look at this, there's actually all these little red lines in here are minor folds and faults. So there's all sorts of minor folds and folds and faults in here, and this is like putting your finger in the cake. So let's put our fingers in the cake and make these other folds and faults. All right, so our cake's getting more complicated now. Let's do a little bit more with this layer cake, and I'm sorry this clicker's a little slow, so and I'm clicking away here. There it goes. So there's a lot of other faults that are named faults, and here's some of those. The Monument Fold, the Red Horse Syncline and Anacline, the Vishnu Monocline, and out further, the Matkatameba. And this is a very slow clicker. Okay, now we have to put in faults. So I think you're standing in front of the thing for my access there. So let's take a knife and put in some faults now. And so we'll go ahead and put in some faults. Okay. And so there are other faults that they have other names. They're through that area. They go not only north, east to southwest, but they also go northwest to southeast. So there are a lot more faults than I can show here, but this gives you an idea. Okay. Because the cake is brittle, there are tons of fractures in all these formations. So let's put in the fractures now. All right. Our cake's getting more complicated. Now, there's over 1,000 breccia pipes. So let's take an ice pick and stab the cake 1,000 times. Or 1,300 times if you want to be more accurate. So there are more breccia pipes. Our cake's getting a little bit more complicated here. And now let's add the 17.5 plus miles of exploratory holes and shafts in the breccia pipe area. And note that these vertical holes are conduits where water can move up and down vertically.
Miles just at the Indian Plate Mine.
Just at the Pinyon Plain Mine, the boreholes for exploratory boreholes are more than 17.5 miles of just the exploratory boreholes. At the one mine, and that doesn't include the access shaft, the big the big hole in the ground that goes down, 1,200 feet, and the spiral for the vehicles to go down, and the big cavities. They're all in addition to the 17.5 miles. Good question. Okay, so now there's hydraulic head differences. We'll put in some pumping in Tusayan. Almost done here. So we're going to pump, and when you pump a groundwater system, it draws water toward it, and so it can take it in different directions. And also they're pumping water out of the mine itself. And so the amount of discharge that they're taking out of the mine is about maybe 8 to 10 million gallons a year. And so we're concerned not only about the water quality, but the water quantity of the springs of the Grand Canyon, because as you know, if you've hiked the Grand Canyon, some of the springs are just small seeps, but they support a whole bunch of wildlife. And so let's throw in earthquakes now.
Like, good.
I kind of like this part here.
Yeah. Oh, good.
You get the idea. And then lastly, subsidence. The subsidence studies were done for this mine were done for just one section in the main mining section, but the highest, that would be over in here. But it turns out that the highest grade uranium is right down near the red wall. And so the subsidence studies didn't account for bigger holes. And so if this collapses, there's going to be some sinking of the ground. So let's sink it down. You can see things starting to sink here. All right, so that's a concern as well. So we'll take these last slides. Let's compare the hydrogeologic complexities of the real system versus the simple layer cake. So here's the simple layer cake of the Bright Angel Food layer cake that the mines have in 1986. And now let's look at the complicated case. And so if we look at that, it turns out that the real Pinyon Plains mine hydrogeologic system is much more complicated. And that's why scientists are concerned, because it's a very simplified model that's being used to predict whether or not it's going to affect the springs. And so we go from this, in 1986 to maybe something like this. So I'm done, and I'll hand it over to my colleague, Dr. Laura Crossey, a distinguished professor at the University of New Mexico.
Thank you. I want to be sure, of course, she's going to get up for the next presentation, which Karl and I, which by the way, we are married, so.
Full disclosure.
Yeah, it's a 24/7 geologic activity that we do here. And like David, the work that I've been doing in Grand Canyon, I've been at the University of New Mexico. This is my 39th year there as a professor. And though Karl's older, I'm a little more senior because I started at UNM while he was still here in Flag at NAU. So thank you for getting that up there. So the work I was doing was more regional. It wasn't directed toward understanding uranium, or frankly, I was not driven by any kind of practical application, basic science. I want to acknowledge the 11 associated tribes of this region on whose indigenous lands we're talking about today, and the Grand Canyon National Park. The work that we undertake has been supported by the National Science Foundation on many different basic geology topics, and of course we work within the park permitting system. So thanks to all of that, and I'm really happy to see Stuart here, because it isn't all of the time that you have your project and your work that you've been working on for decades come to be relevant, and it's been a real pleasure sharing our work and meeting with the tribes by Zoom and by voice, and hoping that we can make some change happen here. So Dave gave such a fantastic overview, and I think he took the right tone, but I'm going to sort of dig in, because we're not going to turn this train around with the general concepts, because it has to boil down to numbers. And one of the aspects I think that's caused some of the action now is that we can point to what we call peer-reviewed literature, scientific literature that's accredited, so to speak, that's come up that really demonstrates that some of these simplifications are not applicable in the region in general and at the mine site as well. And there's people in this room that have contributed to that story. So Grand Canyon, not just a fantastic geologic section, but it's also a beautifully dissected aquifer system. And that was the reason that we came in to work on the groundwater, because where else do you have such a cutaway view in nature with access to the groundwater system? You know, when we try to understand the mixing of waters in the subsurface, it's not as easy as it is at the surface. So there's an aerial view of the confluence where you see two different waters. The beautiful blue-green waters of the Little Colorado River, which is groundwater emerging from a spring upstream in that canyon, and it's flowing and meeting at the confluence with the green water, which is the Colorado River, sort of an interloper coming and sourced from rain and snowmelt up in the high Rockies. So the green water is flowing on through, and the blue water is essentially groundwater. We can see the difference with our eyes. If we go down to the confluence, we can see the mixing process happen. But now we're going to try to describe how can we access water and what can we do to understand mixing in a three-dimensional Tetris system that we can't get our hands on and we can't see. How do we see? Many of the ways that we see water in the subsurface is using geochemistry. And that's what my business is. So like Dave, I'm going to try to think about the geochemistry in a very practical way. And to a very simplistic point of view, there's three types of water in the groundwater system in Grand Canyon. And I'm using these three bottles, which I also have in person here, to kind of represent those. This is the one that we're most interested in. This is the fresh drinking water. We want to obtain this from Thunder River. That's the water supply for Grand Canyon National Park. And there's been quite a bit of groundwater work underway. Even now, as the system is changing, the groundwater supply at Grand Canyon, there's been a lot of work doing to understand the sustainability of this very fresh water that recharges and then comes through the groundwater system, and we're capturing it, and it's good enough to drink. So that's the fresh water. The next water is this one. And I'm using this because it's an electrolyte solution, and we all know it has salts in it. It's mostly H2O, but it does have salt in it. And you could imagine that we can take any amount of the mixture and we can go after that analytically, and we can determine mixtures of fresh water, like recharge water, and the salty water. In nature, as the water travels through the subsurface, it acquires solutes, and these can be benign salts. They don't have to be toxic uranium and arsenic and metals, but they could be. So all different concentrations of different solutes here from water-rock interaction in the subsurface. The longer the residence time, and depending on the character of that rock material, the more laden it's going to be. This is my favorite water. It's mostly H2O. It has sugar and salts in it as well. So it's like those two bottles, but it's got one thing that they don't have. And it's a surprisingly powerful thing, because you're already getting nervous. I wonder how it would look if I actually sprayed everybody, but I'm not going to. So what's this got that they ain't got? It's got the CO2 packed in there. And nature, through a variety of reasons, we have CO2 in the subsurface, and it has affected these waters. What was driving me was to try to understand travertine, the beautiful travertines of Havasu being one example of travertines in Grand Canyon. That's what led us to a recognition of the important role of faults and fractures in this complex hydrology. It's because we were chasing the gas. Here's an example, sampling with a funnel in these effervescing springs. And so it's not really the prime part of our story today, but it led us to a deep understanding of how complicated the system was. Here's just a sort of a simplified example of some locations in Grand Canyon that show us that we have different types of water, different mixtures of these basic types of water in this really broad region of the whole Grand Canyon, both north and south rims. The upper world, the fresh, recharging water, and then the lower world. The waters are warmer, constant temperature year-round. Generally, they have low oxygen. Think back to some of the characteristics Dave was talking about. And they deposit travertine and they effervesce. So instead of showing tables of numbers, one thing that geochemists do is they make little puzzle pieces that show us the shape of water. So we can look at the solutes, those are the ions, the positively charged ions on one side, the negatively charged ions on the other side, and we can make a kind of a shape that we can recognize. So that tells us the character. We can use the solute differences or the shape of this geochemistry to tell us which things have an affinity with each other. So here's just some of the springs in Grand Canyon, and we're just sort of hanging them together so you can sort of see, oh yeah, I see some similarities, which ones are grouped together. Now we don't really do it this way. We do complex statistical models and we use the numbers, we don't use the shapes, but it isn't rocket science. Now I've also changed the scale, like the LCR and Pumpkin Spring are way saltier. They would cover the whole slide. So some waters are extremely salty. Anyway, we can use the salts as tracers. If we, instead of showing them as individual shapes, we can then combine all the waters on a more complicated diagram where we do the cations, that's the positively charged ions on one, the anions on the other, and then we project them in, and we can start to see mixing relationships. So we can use the salts in our different types of Gatorade to examine mixing. So that's just one type of tracer that we use. When we look at the whole Grand Canyon region, of course, we get some kind of craziness. We see different patterns in different regions. Using this geochemistry of the solutes, we were able to look at different subbasins on the North Rim side, on the South Rim side. And this was around for quite a while. This is 2006. The other trick that we use, or the other tool, is stable isotopes, as Dave mentioned, and he had a long track record of working on some stable isotope geochemistry in this region, and we added a lot more. I've just shown a graph of the two pieces of the water molecule, the hydrogen, which the deuterium is the stable isotope ratio that we're using, is the deuterium to hydrogen ratio, and then the two different stable isotopes of oxygen. So we're actually tracking the water itself. So the solutes tell us about mixing and dilution, and the stable isotopes give us a hint about where the water came from, the water itself. So we're using two different aspects of it, but they have to come together. So we call that multiple tracers, different types of tools to help us understand non-unique solutions in very complex systems. What we see here is just kind of fun. Here's the Colorado River. Down at the bottom, it's on a different track altogether. It's coming from Colorado, higher elevation, colder areas. It plots in a different spot on a diagram like this. And I'm just gonna go ahead to the next. This is North Rim waters here. They sit down into the left versus South Rim. So we notice that we see a difference, and this has to do with their recharge elevations and, is one more monsoons, is one more snowmelt driven? There's a lot of complexity in here, but I'm just gonna be very grossly simplified and say, well, we can see the difference between these two waters. Well, the park's been doing an experiment, and that is piping water from the North Rim and using it on the South Rim, using it all over the place. 6 million people a year, flushing toilets, washing dishes, doing laundry, watering plants. So we thought, let's use that signal that the North Rim water is different and see if we can see it in the springs. And again, this is complicated data. We have more details in our very recent 2024 paper, but the bottom line is that we look at where the North Rim is, the North Rim water. Here's an example of a South Rim end member that was up and to the right, and we find beautiful mixing of these two things when we think, so this would be like taking two clear waters, but seeing that they came from different places. So we come up with a picture like this, and this was in our 2006 paper, that we know that we have very complex mixing and that faults and fractures are a really important part of this mixing in this system. So it's data from this, and Karl will now carry on with other data sources that are even more, I think, really exciting and graphic, that show that those simplifying assumptions are not borne out when we look at real data. And by integrating that in 2024, we've sort of, I hope, emphasized the importance of bringing all these studies, none of which were cited or reviewed again during those processes that Sandy talked about. So Karl, are you all set?
Yes.
And there's our three bundles. There you go.
Okay, so I want to try and let's.
Karl.
Oh, thank you. Okay, so I want to try and bring these together, the regional story and the local story of Pinyon Plain Mine a little bit. And we want to be sure and answer your questions. So does anybody want to stop me now and ask a question for Lori or for David? David's the expert, the hydrologic expert on the Pinyon Plain Mine. Lori's the expert on the geochemistry of waters. I come in as a structural geologist because we think the faults and the fractures are really the superhighways for fluid movement. So do you want to stop me and talk about a question, or? Yeah, do that.
Quickly, the origin of the breccia pipes themselves is Jurassic in age?
I don't believe so, but the ages that come out of dating uranium are very scattered, not very easily understood. There's ages that range from sort of middle Jurassic to late Jurassic. I don't think they're correct as the age of the mineralization, but that's a huge question right now.
At a time when those strata were deep under ocean, had been buried.
Yeah, under the Cretaceous Seaway would be the idea, but I don't think that's right. I think it's younger. But the origin of the breccia pipes, which Dave, when he presented the present understanding of that, is in its early stages in my thinking, especially the age. Yeah.
You've explained the complexity of this quite well, but when you read the Arizona groundwater aquifer protection permit, they make it seem very simple that they can manage the risk.
Yeah.
Do you look at how do you look at risk when you're discussing these scientific ideas in terms of the public communication of that, so people can understand risk, and that it's not something that's manageable by technocrats with a permit in Phoenix?
In our opinion, the risk is very high. We're from New Mexico with a uranium mining legacy in which birth defects on the Navajo reservation are rampant and unacceptable. So we're going to come at it from the point of view of how much do we understand about the complexity and how much don't we understand about the complexity, and is the risk justified? Our answer is no. We don't understand the system well enough to quantify those risks, and the risks are so high for the Havasupai tribe, especially with the gradient of the water heading towards that main spring of theirs, that we'd say, we're not risk management people, we're scientists, but we say there's so many unknowns that the risks are unacceptable right now. But Laurie and Dave will comment on that as we go. I'm trying. Okay, here we go. So the gradient thing, I want to just make a couple of points. The old idea was water recharges at the San Francisco peaks, goes down into that upper aquifer, the C aquifer, which is over here on the right, this thing. It drops down by the time it gets to the canyon along these faults. But we've now found the Pinyon Plain Mine has a lot of water in the C aquifer. So we don't understand the connection between those two, and we maintain there is a strong connection. And the Pinyon Plain Mine is a scientific experiment to show the connection, in our opinion. Also, this thing that Lori mentioned, we're dumping water here at the south rim. It's true the layer cake drips to the north. That's their simple tilting. But the head, the water flows downhill. Did anybody notice that? Water goes downhill. Anyway, all this recharge is going to lower elevations, however it can go. And it goes down faults, and it goes along these aquifers till it drops to the next one. So we know from this mixing experiment the park's been doing that water is coming from the water treatment plant here and getting into the groundwater in the RM aquifer as far north as the valley wells almost. So those are interesting. I'm trying to give you a picture so that you can sort of combat, as David did, the simple ideas. So this is from our Boatman's Quarterly paper and our Crossey et al. Recent paper. Just remember that these faults, northwest and northeast, form a grid, and water flows through aquifers, sedimentary aquifers, but this is like a superhighway grid. And so, yeah, water can move parallel to bedding, but it goes across bedding in this grid. And here's the gradient, the Havasupai Springs down here. This Blue Springs is another one in great danger, in my opinion. That's like 70% of the south rim groundwater. All this region goes into there, another 30% there. So those two springs are the ones to worry about and think about. Okay, so this is kind of a simple version of the next slide, but one of the amazing studies that's been done recently was by the park, and Dave's been involved in this also, and we have as well. But if you inject food dye, dye tracers here in the snow, and try and see where it goes, what they found is that water travels very fast, very far along this superhighway network. And now we need to do that more in the South Rim, but our natural tracers, this is where all the different dyes went for different years, and we can come back if anyone's interested. But we think that the stable isotopes are a natural tracer, which shows water comes from the Water Reclamation Plant, WRP, and makes it a long ways along faults. So these are two tracer studies, different tracers, both giving the same answer, which is water travels fast and far along fracture networks. Yeah?
Hi, Karl. That was going to be my question. When you say fast, what do you really mean? Do you mean like it takes a year to go a mile? Because we're not talking about
Months, months maximum for a portion of the water. And Lori's talk tried to get you to think about mixing. And so we can't know how all the water gets there, but we can now say a fraction of the water out here at Vasey's or over here at Pete's can travel in months from a snow recharge here on the North Rim. So some of the water is traveling fast. Yeah, Dave has a comment.
Can I just follow up on that? Yeah. Some of the confusion is that you get different results for different environmental tracers. For example, they've tested carbon-14 in the lower aquifer and the upper aquifer, and the lower aquifer was old in thousands of years, but might be mixing. They tested for freon compounds, the coolants that started in 1932, our refrigerators started leaking in the atmosphere and coming down with rainfall. There's more freons in the deep aquifer than there is in the shallow aquifer. And also there's there's some indications of younger water in the deep aquifer. So when you ask about risk, that's one of the problems, is that there's information that is actually contradictory in some cases, and indicates that there is a certain amount of mixing going on.
I just want to follow up with one more point about this. This is just such an awesome experiment. We did the thing with the North Rim water and the South Rim water, to show that difference. It was an experiment that's been going on for 30 years. It's not controlled. Here's the colors. They put it in. They put in one type in 2016. So the round circles where they put it in. The triangles are where it had hits. What we mean by a hit here is that means that these folks, and Alex is here in the back of the audience, and he knows the work that the group has done, hiking to all these different possible hit sites and putting little tea bags out there. And let's say you put 4 tea bags out there. And it's a lot of work getting to all those different places. They put it in, and of course, what were they trying to do? They were trying to hit Roaring Springs. They were trying to hit the broadside of the barn that was only a few kilometers away, and straight down the biggest fault and down the stratigraphic dip. No brainer, right?
They're trying to hit here.
They were just trying to hit it here, from here. Where'd it go? Perpendicular. Woo! It ain't a simple layer cake.
In a matter of 2 years, right?
Even less.
In months.
So the point is really the water's flowing downhill for sure. They're putting it in the snowpack, and it finds its way down through there, through these complex networks. And it's not going to be the same every year. What if it's like what we just had, this disaster in Florida? You have a couple of monsoons, you have a really wet year, you load up these complicated karst aquifers, and then you have another snowmelt, a big snowmelt on top of that. Whereas if you have a drought instead of 5 drought years, well, then the pathways could be completely different the next time. So it's really, really difficult to model, and that is well known in the hydrologic business.
So one of the things that the line says is that they've drilled into the perched aquifer, the sea aquifer, but yet around Flagstaff, we also have the drinking water wells, like in Woody Mountain Wellfield, is in the sea aquifer. So question on that is there been any study looking at southward migration into town in terms of the effect of contamination or dye tracing studies into Flagstaff. Because part of what the mine has done is try to sow seeds of doubt that they're in a perched aquifer, and they won't admit that it's actually the regional sea aquifer. So I bring that up because I've actually met with the mine, asked them these questions, and they say, no, we're in a perched aquifer.
Let me address that with a couple of figures, and that's exactly where I was headed next. But I did want to mention the earthquake swarm that we've identified. These faults and fractures are all moving, and in small magnitude earthquakes, but they're all under east-west compression, which is what these beach balls over here represents, these guys. The number of earthquakes has increased dramatically as the pumping of water down the water reclamation plant has happened. So we keep this active tectonics in mind. Now let's, oh, look at that.
And he's done.
Go back to,
She needs to start that, get back to the slideshow piece, right there.
While we're waiting for something, I just want to add one more tracer. Uranium has different weights. There's uranium-234 and 238. And they're actually, when it's around the mining activity, very often the ratio is what we call secular equilibrium, where it's close to 1, that ratio. And if you look at all the Grand Canyon springs, below Orphan Uranium Mine and Horn Creek, it's near secular equilibrium, which is another indicator. So there's a lot of environmental tracers that we're not talking about here. And one of them is the uranium isotope ratio, or what's called the activity ratio, between 234 and 238. And so you can sometimes get more, nothing proves anything in science, but what you do is you get more collective evidence, like in a law case. So a reasonable person sees
this is okay.
enough evidence that something is true.
So here's
Something is likely.
So here's the perched aquifer idea, that the sea aquifer, which you see the bracket on the right there, Lori can point at it better than me, as Dave mentioned, is not the Coconino sandstone only. It's all these other units. So they're saying that's perched. And then the regional aquifer is the RM aquifer, the dark blue. There's no evidence. So David mentioned an aquitard in the lower Supai. There's no firm evidence that there's a major aquiclude, which would preclude connections, even an aquitard, which would slow connections between those aquifers. The idea of a perched aquifer, which goes way back in the literature, is simply oversimplified. Now, it's true that water can pond and migrate laterally in the sea aquifer, but believe me, gravity's taken it down. It's taken it down through the fracture network. So the perched aquifer concept we can disprove using stable isotopes. And that's our tracer. And we can show you that the Flagstaff sea aquifer, that water distribution of stable isotopes, is the same as the distribution in the RM aquifer on both the south and the north rim. But I want to give you this picture of the mine itself. Do you see the footprint, the two red things there? The shallow ore body, which they're mining right now, and the deeper ore body, the Juniper one, are straight down below those footprints. And then the wells, 1, 2, 3, and 4, are shallow wells that go only down to the Hermit. They do not get down to the level of the ore. And then the one deep well that, as Dave said, is inadequate to tell you which way the water's flowing. So at present, we don't know the direction of flow in the sea aquifer, the RM aquifer. There's no evidence that it's a perched system above an aquitard, and that we don't know the current levels of contamination of these waters. So as scientists, we say, wait a minute, the risks are too high. These are things we don't know. So this is a nice cross-section we've put together. This one's not published, but just again, to get you thinking about the complexity that Dave talked about, look at the ore body, the red. It goes from way up in the Coconino down to way down in the Supai. So the ore practically itself connects the sea and RM aquifer in a bunch of breccia, in a breccia pipe. So that question mark there, we feel it's very likely that there's a hydrologic connection of the breccia pipe itself. And then the deep wells that go down there, some of the early exploration wells already showed saturation through that area that they claim is an aquitard. So The view of two separate aquifers, I think, is incorrect. They're connected by faults and fractures. And then look at the groundwater levels in the sea aquifer itself. The saturated part is down well below the hermit. This hermit is not a confining layer or a aquitard between it. So the point is there's a cone of depression now. This adds this idea. As they pump 67 million gallons since 2013, the present water table, if you let me use that word, is very depressed as they're pumping water out at a significant rate from the sea aquifer. So we think that those question marks are too big, the risk is too high, and our recommendation, I think, is shown in the next one, which is revoke the aquifer protection permit, require new EIS, request federal review of mining decisions from the Arizona Department of Environmental Quality, establish better monitoring wells. You've got to have multiple wells that penetrate through the sea and RM aquifer. It's not there. We don't know how contaminated the water is or how fast it's moving or in which direction. Now that's unacceptable for us as scientists given the great risks to humans, to springs, to ecosystems. So we'd like to see a meeting with the Secretary of the Interior. We'd like to have it include the Havasupai tribe scientists, Arizona ADEQ. In other words, a consortium approach, which I think the Sierra Club has been fantastically successful at promoting. We have to work as a team and get these different perspectives. Our own perspectives as scientists are that all of these things should be discussed. So I want to open it for questions.
Know of any of this work that you're doing, and has she said anything about how she feels about it?
She's from New Mexico. She's from from our home state. I believe she's more attuned to the indigenous issues than any past Secretary of State, since she is herself from Secretary of the Interior. Is that who you asked about?
Yeah, definitely.
Yeah. So I don't think it's impossible. She's busy with other things, but I think there's word trickling up that it's a major concern. So maybe a letter or two.
I think the Havasupai have tried reaching out, probably, and it's just a heck of a time, isn't it, right now?
Yeah,
trying to get
we've
some
done
of
it
it.
within the last couple of months.
Yeah.
We did actually make contact with Deb Holland, so our tribal leaders were just recently up there. But yeah, she's receptive toward it. One of the first people that we had spoken to when we came to the National Monument was Deb Holland, so she's familiar with the actions of Pinot by Mine as well as tribal efforts as well.
Representative Grivaldo from Arizona, he's the fellow who put together the 2012, just before the 20-year moratorium, put down, the tribe was there, the experts were there as well, the mines were there, and they all testified before Congress on this issue. So there is also congressional support for this sort of thing as well. In addition to that, the three of us have also had conversations with the Arizona Department of Environmental Quality, and they're continuing. We've had conversations with the Arizona Attorney General and with the governor's office as well. And so that's ongoing because many times they want to know about the science, and we can answer some of the questions for them. All right.
Are there any comparable cases where, the sanctity of the 1872 Mining Act has actually been stalled or thwarted by environmental concerns? Or any parallel kind of situations that exist legally?
Larry mentioned the 1872 Mining Act. For those of you unfamiliar with it, it allows the mines great leeway in going on lands, federal lands, and staking claims and drilling wherever they want, and pumping out enormous amounts of water if they want.
And not giving the information, even to the regulators.
That's right. There's not information available in some cases in the mining activities that are going on because they're privileged. I've worked in cases in Nebraska, and the mining law is so strong that it's hard. There really needs to be a change in the 1872 mining law because it is so strong.
And both Grivalda and Heinrich do have a new mining act in Congress right now that proposes to revise that. But, maybe this could be the poster child. I'm not aware, Sandy, do you, or Taylor?
Yeah, there are a few cases, and the cases where another law has superseded the mining law have involved the Endangered Species Act, and only in instances where there are very pronounced threats from that mining to an endangered species. That case law has been building in the last decade, but the instances are still few and far between.
One other thing that's a modification of that is the mines can't take their spoils and put it on another property that's not on their claim. And that's actually pretty strong. The strongest hammer is the Endangered Species Act. But the fact that the mines can't spread out the tailings all over the place is also a restriction that's been proven in court.
Yeah, and that was another Arizona case on the Rosemont mine in southern Arizona. And
Recent ruling in the last year from the Supreme Court of the United States.
One of the things I reached out to BLM, and they noted there's 600 claims that are grandfathered in the new monument that could be acted upon. So really what happens here will determine the future of those claims in terms of, even the monument can't stop down under the 1872 law. And then there could be court case that said, if you did change the law, that it's a takings clause violation if they were to remove that right to the 600 claims. And with the price of uranium skyrocketing due to the geopolitical issues in Russia and the war, it's just incumbent on getting this right. And it seems like there's just so much uncertainty in the science. Yet here we go once again, where you have a multinational foreign mining company coming in and wreaking havoc on the area around that's so sacred to so many different people. So I just bring that up because there's 600 claims that could be acted upon right now.
Yeah. So just a clarification on that. In order for those claims to be developed, the mining company has to demonstrate valid existing rights and establish valid existing rights. And the only way to do that is through exploratory drilling that Dave showed. So while there are hundreds of claims up there, there are only a handful that have been explored that could be eligible for establishing those valid existing rights. And the last date at which exploration could have happened was in 2009 or 8, when this area that's now the monument was first segregated. And at that point, there were, I think, 6 to 10 claims that had been explored that the Bureau estimated could possibly someday become a mine because valid existing rights have been established for. So
that's not what BLM is saying.
Yeah, their own FEIS for that withdrawal lays out very clearly. So I think they're misinformed, but that's not to say that when Energy Fuels is potentially done here, they won't go elsewhere. They have several claims up on the north side as well. So I think they're overstating it, though.
A couple of things before we get to that question. Just hang on a second. One question: it's a large multinational with a U.S. subsidiary, and so a lot of the companies that come in are large multinational ones. And you mentioned that. Other things associated with that is that there's a lot of breccia pipes that are not in the new national monument and are still in the Grand Canyon region that are not protected. And I mentioned very quickly a 20-year moratorium. In 2012, the Secretary of the Interior from the Obama administration put a 20-year moratorium on new mining while the science was developed by the U.S. Geological Survey and other people. And so most people here know that, but there's maybe some people who don't understand that there's a moratorium on new mining. And there were 5 mines grandfathered in during that period. Question over here.
From me?
Yeah, somebody over here, I think.
Sure. Yeah, I have two. One is like how. So there's big cleanup at the Orphan Mine. How clean is it today? Not very healthy. And then my second question is, because Havasu Canyon is such a long, deep canyon, is it possible that because the aquifer is split around Havasu Canyon, the waters on the west side of Havasu might be safer from uranium from the Pinyon mine?
That's a great comment.
Yeah, in terms of the drainage basin for the Havasu Springs, it's the Cataract Creek drainage, which is immense. And so the water flows downhill. I mean, it just does that. And the gradient of the aquifer and of water that moves along fractures through the aquifer is from the Pinyon Plain mine to the cataract system. Now, how fast it gets to Havasu Spring and at what level a contaminant plume would move are some of these unknowns. Now, it's true that the west side of the cataract system has its gradient also back toward the east. So you're right. The contamination from the Pinyon Plain mine would affect Havasu Spring, but so would breccia pipes coming the other direction from the well pipeline.
From a hydrologic standpoint, there's a paper that just came out 2 years ago of USGS, Peter Amtoon and others, and they say the recharge area for Cataract Canyon, which is also Havasu Canyon, just another name for it, is bigger than the state of Connecticut. And it actually flows according to the maps that have been drawn in that recent paper 2 years ago. It flows past Pinyon Plain Mine and Tusayan and goes right out to Havasu Canyon. And so that is the potential recharge area that the USGS has recently identified. And then there's been other isotope studies that show a connection between the two aquifers. And as far as whether it's dirty right now, the water they're pumping out right now has been well above uranium drinking water levels and even higher above arsenic levels right now. And there's possible reasons for that with the oxygenation that goes on the lining and other possible reasons why, when you put tunnels and things like that, you add oxygen to the system. And remember, more oxygen means that the solid stuff goes to dissolved phase in groundwater, and then it gets legs and moves through the system. And so that's one possible concern that really is not been modified.
And her other question is that the Lost Orphan mine, it has not been adequately needed.
The Lost Orphan mine, yeah, I've been studying that for a long time, before you were born. And it's persistent high uranium. One of my master's thesis from last year saw a negative correlation between rainfall and it's Phantom Ranch and concentrations. In other words, when there was low rainfall, the concentrations were higher and there was less dilution. Whereas when there was more rainfall on Phantom Ranch, the concentrations were lower, coming out from below the red wall, just below Orphan Uranium Mine. So that Horn Creek drainage, though, in March of 2023 was the end of that student's thesis. The springs were contaminated all the way down into the Vishnu schist, the lowest layers, all the water coming out through the Horn drainage. So there's a legacy here and a time bomb effect that there's something called the precautionary principle, and certainly that's something that at least people should think about.
Well, this is very frustrating because the taxpayers paid a whole lot of money to clean up this site and it's still not clean.
But that's right. Good point. Well, we're running down on time here. A question in the back.
So the little Colorado River that runs through Cameron and stuff, there are some open pit mines along the shore of that little Colorado River, and it actually flows into the main Colorado River. Now, are you seeing any of that isotopes from there in your study?
There's a great dilution factor in the Colorado River because the river comes down from Lake Powell, and such a tremendous amount of water comes down that even if there is a pollutant, it's less likely to affect the Colorado River main stem itself. The little Colorado River, I guess there is a potential for problems with that. But
So that would affect the true springs, though.
Definitely. But if I could just say about the stable isotopes, I'm not showing it, it's a little technical, but that same diagram Lori showed shows that the little Colorado River is a alluvial aquifer. So if you think about the water that's close to the surface near the little Colorado River, that water is way up and to the right on the diagram, the stable isotope diagram. And it is definitely mixing down into the Blue Springs system. So I have a sort of a secondary thing besides Havasu Spring. I think Blue Spring needs a monitoring program right now because it's 60% of all the water that on the south rim, maybe 68, I don't remember the exact number, that comes out of Blue Spring. It's endangered. We don't have a baseline for what that water is, how it changes year to year, and what the possibilities are for existing contamination, let alone future ones. So it's a very important spring.
I would like to modify that just a little bit, because if you hike along the Tonto Trail, there are all these small springs with unique little habitats where there are frog symphonies at sunset, and they're beautiful little places. And some of the animals, bighorn sheep and birds, they can move, but some of these species can't move from these little oases. And even though the big springs are very, very important, the amount of water that they're pumping out of Pinyon Plain, if there is a connection with some of the small springs, and the Vishnu Fall, which goes through Tusayan and not too far away, just a couple miles away, goes right to Grapevine Spring. And so if you're pumping out millions of gallons, and some of these springs are less than a gallon, but they support a huge amount of wildlife, that's a problem. The amount of water they're pumping out, it could the amount of water that comes out of like 50 springs in the Grand Canyon we haven't established a connection. It's just an example of the quantity of discharge from the springs and the quantity that they're pumping out. So if those little springs are impacted, that could be really pretty bad. The big ones are important too.
Got to monitor them all.
Yeah.
Yeah, the more monitors, the better. But some of the arguments are going to be and have been based on comparing those wells. Karl showed wells 1, 2, and 3, which are in the Coconino, and the main mining is in some cases below that level, right? So the monitoring wells there will be diffusion from this really highly contaminated water, which isn't really surprising. Think back to the Gold King mine spill. The water that resides in the actual mined areas is uber nasty, and it's not like anyone was thinking that would be drinkable, right? But it will diffuse out. And if you don't have the cone of depression anymore, keeping the fresh material coming in, then that can diffuse out. And if there isn't a fault, like right on the mine property, which we keep hearing, but the fault is over there, that contaminated water can still, it'll move into that pool. It'll be somewhat diluted potentially, but then it still will have access down. So, you can't use arguments about what's in the couple of acres of a fence and say, well, we're not seeing it straight down underneath. We're not seeing it in that deep well, right in the same spot. Well, the water that went in the dye tracer studies moved 35 kilometers in one season off-site of where they poured it in to a sinkhole.
Does the dewatering also increase the concentration of the dissolved uranium? And that was a question I had for ADEQ when they were studying the aquifer. I think they call it the AQL limits, that by actually dewatering the aquifer, they're removing the dilution factor for the dissolved solids. Is there any study on that in terms of?
No. The deep aquifer is really strange. Say just simply you had 2 cave passages. It's a limestone. And in one cave passage you had contaminated water, and another one you had clean water, all right? And the deep well, the one monitoring well they had, say it was drawing from both, all right? And so even if they picked up contamination, it would be diluted and it would give a false negative. The last thing, you know, I gave lecture series around the country for how to design monitoring wells for the Environmental Protection Agency. There were 3 of us and we did 2-day seminars all around the country. And in the simplest hydrology, the simplest one, where everything's homogeneous, to get the direction of flow, you need mathematically 3 wells. In other words, think of a slope. If one well level is up here, and another well level is up here, and another level is down there, you know that the water's going downhill this way, all right? If you have just one well, it could be going in any direction at all. And so one well is really kind of inadequate because of the dilution, possible dilution factor. You know, the amount, they say that, you know, the uranium amounts are not really high in the lower well yet, but they have varied tremendously in the times they've measured the deep well. And the problem with that is if they don't give us the pumping rates, say they're pumping a lot and they get a low rate, and they're pumping a little, but the mines don't release the levels that they pump out before the antecedent pumping and things like that, which a scientist really needs.
It's my understanding that their requirement is to analyze that annually. That's well. And the USGS has to inform the mines when they're coming. And that well is used as a water supply well to wet the roads, to keep the dust down, to do all kinds of other things. And it's just like any other system, you know when someone's coming, do you have the opportunity to maybe somewhat perturb things? But, there is, it's not like that. I think we do have to be careful and say we don't know that there's any contamination. There hasn't been any recognition of anything at Havasu. We don't want alarm bells to disrupt people's ability to have their economic resource of their tourism affected by, concerns. The concerns are here to stop the mining, but it hasn't gotten anywhere yet from that.
There is some natural contamination in some of the springs, just because of the geology. And Havasu is an example where arsenic's been kind of high, so they have a treatment system there to take the arsenic out, and that preceded the mining operation. The recognition that it was there. One of the arguments too, one thing that we didn't mention, the 3 monitoring wells in the upper aquifer. If you look at the levels now, they're being affected by the pumping in what's called the cone of depression that Charleston's in. But if you were to look at the direction of flow, hit me over the head. If you look at the direction of flow right now, it's to the east-northeast from those 3 monitoring wells. So if you talk to the Arizona Department of Environmental Quality, what is the direction of flow in the upper aquifer right now? They say, we don't know. You can't get us to shut up.
Well, you can talk some more as we pick up, but I'd like everyone to please give a round of applause. So much good information, and yes, it's just not worth the risk, right? Yeah, it's just not worth it. I did want to give Mateo just a moment to come up and talk about some opportunities to get involved. So,
thank you so much for coming here today. We really appreciate it. Just a reminder that I'm based here in Flagstaff. I'm a Grand Canyon program manager, and so if you're really interested in this and want to get involved, want to organize some things yourself, please let me know. I can help you do that, whether it's protest or art education, and we can make that happen. I put out some cards in the back if you want my information, and feel free to give me a text or email. Thank you.
Could we please give the Sierra Club and the other sponsors